Hello everyone, you're welcome to this channel. Today we shall be looking at numerical solution for partial differential equation. We have looked at numerical solution for algebraic as well as for the ordinary differential equation. But today we shall be looking at numerical solution for partial differential equation because in process modeling, some of our models result into partial differential equation. That means the variables or independent or dependent variables are varying in different more than one direction. So let's look at this Cartesian coordinate. So let's look at this Cartesian coordinate. So we can use this coordinate to see that if you have a function that is known at this point, then we can know this point because we have known this. Or if you don't know this and we know this, then we can as well know this as well. Similarly, we can move all through to see how to know anyone, whether previously or ahead. So what you need to know again is that this represents a partial differential equation because it has two directions, the y direction and it has the x direction. So that means our function is moving in different direction, in two directions simultaneously. So at this point, it's moving at a particular y and j and x, and at this point, it's at a particular y and x. So that means it's moving in y and x direction. So basically, we tend to try to represent the value along the index along the y direction with j and the index along the x direction with I. So we shall see how this is implemented in finite difference for partial differential equation. To carry out the finite difference analysis for partial differential equation, we basically employ the Taylor series. Taylor series is a kind of expression that we use to find a function at any particular point because we know it at a particular point as well and before. So we know it at x, we want to know it at x plus 1. We know it at y, we want to know it at y plus 1 or y minus 1 and so on and so forth. So therefore, the function moves in y direction as we showed before. It can move in y direction and it can move in x direction as well. So this is the expression for the x direction. So ui plus 1j, that is, if you want to know when it has moved in x direction by 1, it has risen by 1, then you have to know it in the actual x before. Yeah. So this is x plus 1 when the y is constant, and this is x and y. So u is known, we want to know u at x plus 1, that is a step in the x direction. So because we have known it in the x direction, at x and y previously, so the Taylor series is saying that to know that, you need to pick the last one you know, plus the difference in the x direction, the step size, and the differential at the last direction you know. And you want to make it more accurate, you still go further to the second order differential and so on. So similarly, if you want to know it at a previous direction, you know it at a particular direction now, but you want to know what it was before it get to this point. You use it like the ui minus 1, that is when you want to know x minus 1 step size before. So it's equal to the previous one minus delta x, the ux, the ux, and so on and so forth. Now, what you notice is that the series has infinite number of terms, going from first order differential, second order to higher order, and so on. The more of this time, the more accurate the series is. So if you want it to more accurate, then you have to add more time. But because of simplicity, we tend to limit to whether first order or second order or whatever order we want, and consider the others as insignificant. So from this Taylor series in the x direction, if you want to know du dx alone, then the algebraic expression for it is given as this. Everything is by manipulation of subtraction of the forward direction minus backward direction, backward position and forward position. So by doing that, the equation is saying that to know the dux dx, du dx, at ij position, then you have to know ui plus 1j at ui plus 1j minus uij divided by delta s. I've earlier explained what is ui plus 1. That means the step ahead of uij. So also, you can also use another formula depending on the one that is easy for your computation. It can be uij minus ui minus j. So this one is called forward differencing. Forward differencing, that is, we look ahead, ui plus 1. This one is called backward differencing. Backward differencing, because we look backward at ui minus 1j. So, and this one is called central differencing. Central, because we try to look at the point before and the point after, the point after and the point before, and divide by 2 delta x. So all of those things can be used to approximate the u dx. So similarly, if you want to find an expression, algebraic expression for the second order, like this one, in the x direction, then we can also manipulate it by adding the two equations. We can get something like this, in which case we have the backward direction minus 2 at the central plus forward direction divided by delta s square. So all those expressions can be used to substitute for your du dx in your actual model. That's what they mean. So they can be used to substitute for du dx in your actual model. Similarly, in the y direction, we have just looked at the uh, x direction. In the y direction as well, you can see that now we are now varying j plus 1. When we are dealing with x, we kept constant the j. All our j are kept constant. All our j are kept constant. But now we are looking at the j direction. That is, it is now moving in the y direction. So we kept our x direction constant. So that is what we are having now. So the u dy in that direction is given as follows: uij plus 1 minus uij divided by delta y. So similarly, if you don't use that, you can use this as well. You can use this as well, which is, so this is its own forward, backward. This is its own central, as well as the second order differential in the y direction, in this direction. So that is that. So let's look at an example to illustrate what we mean. Imagine a beaker of radius r, 1 centimeter and 5 centimeter high, open at the top with only air inside it. A certain gas A at a concentration Ca is equal to 1 kilomole per meter cube start flowing around the beaker. There's the diffusion of A inside the beaker, but at the bottom Ca always remain equals to 0. Assume that the mass diffusivity of A in the air is this, dA, that's subscript A. So dA equals to 0.018 meter square per hour. The equation that represents this system is presented below. This equation. Use the finite difference method to obtain the axial profile of the concentration of A inside the beaker over time. So this is a diffusion problem or diffusion model, and the expression is given here. You can see it's a partial differential model. The CA dt. So CA is varying with T as well as X. So it's varying with time. So this time will now represent our Y, and it's varying with X in position. So it's varying as we move in the X direction, and as time changes also, it's also varying too. So that gives it a partial differential condition. So let's see. So this condition are given at t is equal to 0, Ca is equal to 0 for 0 less than 0.0 meter, 0.05 meter. So all of the position was 0. So at x is equal to 0 meter, that is on this x direction, Ca is equal to 0 kilomole per meter cube. It's always 0 at the point x is equal to 0. For t greater than 0, so it's always 0. So that is at all time after t is equal to 0 is always 0. Then at x is equal to 0.05 meter, that is at this point, let's say this is 0.05 and this is 0. So at this point, Ca is equal to 1 for t greater than 0. That is, at t is equal to 0 point here, it is 0. But after t greater than 0, it remains 1 here. For this one, it is 0 here. That's what it means. So, and for this level, it is 0 all through. That's what this first condition is saying. It is 0. This is the first condition. This is the second condition. And this is the third condition. So, let's dive into action and see how our formula can be used. So, the formula we are looking at is dCA dt equals to dA d square CA dx square. So, and we have taken, what we have to know is that we have taken our t to be the y, and we have taken our x to be the x. So that means we are going to look for this expression, the CA, the t, we have to substitute it for algebraic expression. We have to look it in the y direction formula. And for this one, we have to look for it in the x direction formula. So let's look for this y direction formula as I showed you earlier, where j plus 1 is varied. And this is the one for the x direction. So where I is the one varying, I plus 1, I minus 1, and so on. So let's look for the dCAdt, let's look for the y direction. So we can actually use any of the formula that represent du dy. We can use for du dy because we are looking for the CA dt. So, but let's look for the one that have, let's look for the second one here. Let's look for the second one. Or we can as well use for the first one. So I'll go for the first one. You can go for anyone, as I said, depending on the data you have, but any of them will work comfortably. So the CA dt will now be represented as the CA dt equals to, let's look at the first one. That will be CA I j plus 1 minus CA. So let's use that one. So the CA dt will be CA I j plus 1 minus CA ij. Let me just be using C actually instead of A so that it doesn't become clumsy. So CI j plus 1 minus Cij, that our U is now our C now, minus Cij divided by delta Y. So delta Y, which is our delta T now. Delta T now. So because our T has been taken to be Y. So that's that. Then let's find the expression for this one. But you remember this is the square CA dx square, which is in the x direction. So we have to look for that in the x direction. The square CA dx square. So we have to look for that one. So it's only one expression for the second product. So that means it's going to be CA I minus 1j minus 2CA ij plus CA plus CAI plus 1j. So it's equal to CI minus 1j plus, minus 2CIJ plus 2CI plus 1j plus 2CI plus 1j. Everything divided by delta x square. It's still our x, so we retain the x, delta x square. So having done this, so we can now simplify our expression. That means we can substitute this for here, and we substitute this so here. So what do we get? It becomes Cij plus 1 divided by, minus Cij divided by delta t equals to Ci minus 1. So we can now say, then we can now rearrange the formula, this and this. We can rearrange the formula to get something like this. So Cij plus 1 is equal to all of this delta t, dA divided by delta x square. So that is delta t goes there. So this is it. Delta t goes here. It meets the delta x square there. And remember, there is dA here. Don't miss it out. There is dA here. There is dA here. So that's what we are seeing here. So all the constants have now been assembled. dA, delta t, delta x square. And we now have all our expression ready. So we can make it simpler by just saying delta t. We already know data. We know the dA is already given 0.018. Delta t is taken to be this delta t is just a step size which we take a very small number to represent. Then delta x, which is h, is equal to. So when we evaluate that, we are going to get 0.09 for all the constants together. Therefore, our Cij plus 1 is equal to 0.09 Ci minus 1j minus 2Cij plus Ci plus 1j plus Cij. So this is what we are going to evaluate to get our final answer at the point needed. So to do that, we need to keep supplying the values one after the other. We have our formula standing as Cij plus 1. Cij plus 1 equals to 0.09 Ci minus 1j minus 2Cij plus Ci plus 1j plus Ci plus 1j, everything plus Cij. So that's the formula we need. So, and we have to apply all the boundary conditions in order to make this thing work effectively. So we need to iterate just like we did in the last tutorial for ordinary differential equation, and it's going to be a very long thing. So what I will advise now is for us to switch to Excel to help us with this computation very easily. So let's switch to Excel. So this is the Excel page here. We have the equation and we have the conditions. So let's set it up for the solution. Now, we have our t in hour, and we have our x. Let's look at the question once more. The question is saying, imagine a beaker. The height of the beaker is it has a radius of 1 centimeter and height of 5 centimeter. That's 0.05 meter. So we want to work at the diffusion inside the length, which is 5, because we are looking for the axial profile of this concentration of A. So that means we are looking at it from 0 to 5 centimeter, which is 0 to 0.05 meter. And we have taken our the step size along the x direction to be 0.01, and the time along the time direction is 0.0005 hour. So we make it small so that, so let's put it like this. Delta x, that is delta x or K is equal to 0.01, and delta T, which is, delta X is K. K equals to delta X. So then delta T. So we have delta T, or sorry, I think H equals to this. H equals to this, and K equals to delta T. So we have taken this one to be 0.0005. So let's put it like this. Our T is here. Our X is 5 centimeter. So that means we have to say it starts from 0 and is increasing by 0.01. So that means the next X will be 0.01, followed by 0.02, 0.03, 0.04, 0.05. That's along the X direction. Then T is 0. So it's changing by this step size. So which means it's equal to 0 plus whatever is happening here. So we can, then we have to fix D because that is our step size in that direction. So we can extend anytime we want. So now we have to apply our boundary condition. We have to apply our boundary condition. What's our boundary condition? At T is equal to 0. At T is equal to 0 here, is saying that what? Our C is equal to 0 for 0 to 0.05. So that is all of this is 0. Everything is 0 at T is equal to 0. So then the second boundary condition say at X is equal to 0, C is equal to 0 for T greater than 0. That is at X is equal to 0, which is this point, for T greater than 0, then everything is 0. C remains 0 forever. So forever it remains 0 down. Then the last one says at X is equal to 0.05, the last point, C is equal to 1 for T greater than 0. That is, at the last point here, T is equal to 1. Sorry. This is we start measuring the tube or the channel from the bottom up. So that means the top where the diffusion is taking place or start to take place is the 5 centimeter. So that means we are only left with all this region to calculate now after we have applied our boundary condition. So we need to import our formula. So this is our formula saying that to find the Cij plus 1, you need to multiply 0.09 Ci minus 1j. Let me explain this. To find the Cij plus 1, that is where you are currently that you want to calculate, that's your Cij plus 1. That is your Cij plus 1. Now, it's equal to find the value there, you need to multiply 0.09 by all of this. What is this? Ci minus 1, that is you move left or backward in I because you are at I currently based on the formula. You are at I, j plus 1. So to find Ci minus 1, you have to move left or backward. And you have to move backward too on j because you have to subtract 1 from I and subtract 1 from j. So you have to move up backward, you have to move by left backward, left on I too. Minus 2 Cij, you are on I currently. That means you have to move, you have to remain on I at the place you are, but you have to move j backward because you are at j plus 1. Your j should be a step behind. Then similarly, for I plus 1, you have to move forward on I because you are at I currently. You have to move forward on I. Then you have to now move, for j, you have to move backward because you are on j plus 1 currently. Similarly, for Cij, you are on I currently, you have to move backward on J to get the value. So let's implement that. This is our Cij plus 1 now according to the formula. So to calculate it, we have to say equals to 0.09 according to the formula multiplied by Ci minus 1J. So since we are at Ij plus 1 now, formula is Cij plus 1. You are at Ci plus J plus 1 now. So the Ci minus 1J will now be what? Sorry, let me show the formula so that you can follow. So 0.09 multiplied by Ci minus 1. You are on high now. Show it clearly, sorry. So it's equal to 0.09 multiplied by, you are on I now. So I minus 1 will now be a step behind, a step to the left. So that means you are talking of, and J, and it should now be J, which is what? Because you are on J plus 1 now. So it's here, I minus 1 is here. At J, because you are on J plus 1 here. Therefore, your J will now be at this point. So that is I minus 1, J. Okay. Minus 2 times Cij. You are on I now and J plus 1. To get J, that means you are on I here and J plus 1. So your J plus 1 is here. You see sorry, your J is there. Because here that you are is on J plus 1 at I. So this is your I, the same position, 0.01, but J minus 1, that is J plus 1 left subtracted by one step. So then plus Ci plus 1. Ci plus 1, you are on I currently. You have to add, you are on I currently. You have to add, that is like you are going to 0.02. You have to add 1 to it, 0.02. But at J, so that is 0.02 instead of 0.005 of time, you have to put it at here. So that is what the third term is telling you. Plus what we now have is Cij. You are on Ij plus 1 now. Your I is the same spot, but J will be a step behind. So that is that. That is that. Once you get that one right, then you are good to go. If you drag it to this point, everything becomes 0. If you drag it down, it will calculate itself all through, and you will see where you are now having value all through for your solution. So I believe is quite clear. Is quite clear. So those are the. So what you need to do is to take pain to make sure you calculate the first point correctly. To make sure you substitute it correctly. As I said, the formula says you Cij plus 1. When you use your own, when you are trying to substitute from what we have done earlier, your own may not be Cij plus 1, it may be Cij minus 1. So that means Cij minus 1, wherever you are, in your own case, is Cij minus 1. If it is Ci minus 1G, that means wherever you are calculating is your Ci minus 1G. So you have to now move according to what you are calculating now. So please take note of that. Since our formula is saying Cij plus 1 is equal to all of these, that means wherever we stand is our Cij plus 1, and we have to now substitute for all the value accordingly. You have to know where you move backward on X, you have to know where you move backward on Y, where you have to move forward on X and move backward on Y, and so on and so forth. So I believe this is very clear to all of you. If so, please subscribe to the channel, and any comment you have, kindly post to the comment section below. Thank you.